There's a law that governs literally everything in the universe, from the tiniest atom to the biggest galaxy. And here's the kicker. It has absolutely no known exceptions. We call it the law of conservation of energy. But what makes it so incredibly strange is that it's not describing a physical thing you can point to. It's an abstract mathematical principle. And to really get it, we have to start with a question you probably think you already know the answer to.
So let's just ask it, straight up, what is energy? It powers our entire world. It powers our bodies. It's everywhere. But can you actually picture it? Can you imagine holding it in your hand? What does it look like?
And hey, if you're struggling to come up with an answer, you are in some very good company. The legendary physicist Richard Feynman himself, one of the greatest minds of the 20th century, flat out admitted that our best science has no concrete picture of what energy actually is. It's a fundamental mystery right at the very heart of reality.
We all kind of have this image in our heads, right? Of energy as some kind of glowing, shimmering substance, a blob of stuff. But that's totally wrong. Physics tells us energy isn't a thing at all. It's just a number, a single number in a cosmic ledger that, no matter what happens, no matter what crazy transformations nature goes through, that number stays exactly the same. It's an accounting principle, not a physical object.
So if energy is just some number that never ever changes, how in the world do we wrap our heads around that? Well, to make this completely abstract idea feel real, Richard Feynman came up with this fantastic analogy.
I want you to imagine a kid, let's call him Dennis, who has 28 blocks that are completely indestructible. Every day, his mom leaves him in a room to play with them. And at the end of the day, no matter what Dennis has been up to, she counts the blocks. And she always finds 28. This is her one fundamental unbreakable law. The total count is absolute.
But then, one day, she counts, and there are only 25 blocks in sight. Now Dennis, being a bit of a rascal, has hidden the others in his toy box and won't let her open it. So, does she give up? Nope, she gets clever. She knows how much the empty box weighs, and she knows each block weighs 3 ounces. So, she weighs the whole box, does a little math, and creates her first abstract calculation to account for the blocks she can't see.
And things just keep getting more complicated. Now Dennis is throwing the blocks into some dirty bathwater so she can't see them at the bottom. But she adapts again. She knows that each block she puts in raises the water level by exactly 1/4 of an inch. So she just adds another new term to her growing formula, this one for the height of the water. And guess what? When she adds it all up, the total is still 28. You see what's happening, right? Eventually, the mother pretty much stops looking for physical things altogether. Instead, she just calculates this complicated formula full of abstract terms. But that formula always, reliably, gives her the exact same number, 28. And this is precisely how physicists treat energy. This simple story about Dennis and his blocks is a perfect little model for how physicists approach the real world. But this is where the analogy takes a truly mind-bending turn.
In the real world, in the law of conservation of energy, there are no blocks. The physical things we started with, the things we were trying to count in the first place, they don't actually exist. So instead of blocks, physicists have formulas for all these different forms of energy. There's a term for kinetic energy, which is motion. There's a term for gravitational potential energy, which is about position. There's chemical energy, nuclear energy, even mass itself, thanks to Einstein's E=mc². Each one is like the toy box or the bathwater. It's another term in this grand cosmic formula. And when we do the math and add them all up, the total never ever changes.
Okay, so this is kind of wild, right? All of physics is built on a law about a quantity we can't even really define. You'd think this would be a massive problem. But it turns out, just knowing that this number is always conserved, well, that's one of the most powerful tools we have for figuring out how the universe works.
Let's see this power in action. We're going to do a little thought experiment. And we only need to agree on one simple thing. Perpetual motion is impossible. You can't get something for nothing. Got it? Okay. Now imagine we have a perfect, 100% efficient, reversible machine. We'll call it machine A. Then someone comes along claiming they've built machine B, which they say is even better.
Now, just by using pure logic, we can prove things about how this machine must work without ever looking inside. Let's say our perfect machine lowers one ball by 1 foot, and that lifts 3 balls on the other side by some distance x. Well, 3 times x cannot be more than 1 foot. Why? Because if it were, you could hook the machines together and create a perpetual motion machine that lifts weights for free. And since the machine is perfectly reversible, 1 foot can't be more than 3x either. Therefore, 3x must equal exactly 1 foot. And bam, we just derived a fundamental law of levers without knowing a single thing about gears or pulleys.
This principle gives us these incredibly elegant shortcuts for understanding the world. Check out this famous diagram from Simon Stephens's tombstone. It's a chain draped over a prism. Now, since it's perfectly still, it's in balance. And the part of the chain hanging down at the bottom is obviously balanced with itself. So that means the longer, gentler slope on one side must be perfectly balanced by the shorter, steeper slope on the other. It's a beautiful visual proof for the laws of an inclined plane, figured out just from conservation principles.
So we know that this law works. We've seen how it gives us these amazing insights. But this all leads to the deepest, most fundamental question of all. Why? Why does this law even exist in the first place?
The answer? Well, it comes from one of the deepest insights of modern physics, and it is truly profound. Energy is conserved because the laws of physics do not change over time. Just let that sink in for a second. The fact that the law of gravity works the same way today as it did yesterday and as it will tomorrow, that is the reason energy has to be conserved. This fundamental symmetry of the universe, the idea that the rules are the same always, is mathematically tied directly to the law of conservation of energy.
And this is just one piece of an even bigger, more beautiful picture. Energy conservation is part of a whole family of laws, and each one is tied to a different fundamental symmetry of the universe. So just like the laws being the same over time gives us conservation of energy, the fact that the laws are the same everywhere in space gives us conservation of momentum. And the laws being the same no matter which direction you're facing, that gives us conservation of angular momentum. It's this incredible interconnected web of principles that forms the very bedrock of our reality.
Okay, let's bring this grand abstract principle back down to earth for a minute. What does all this actually mean for us and for our future?
Well, this brings us to a really crucial distinction. Just because energy is conserved, that doesn't mean it's all useful to us. Think about it. The oceans contain a staggering, almost unimaginable amount of heat energy in the random jiggling of their atoms. But that energy has very low utility. We can't just easily grab all those jiggling atoms and get them to march in the same direction to do useful work. The laws of thermodynamics, of entropy, they govern what energy is actually available for us to use.
You see, nature is a perfect accountant when it comes to energy. She conserves every last bit of it, but she is not at all worried about efficiency. The sun unleashes an unbelievable amount of energy, but only a tiny fraction of it, 1 part in 2 billion, actually hits the Earth. And pretty much all of our energy, from the rain that drives our power plants to the ancient sunlight captured in coal, it all ultimately traces back to the sun.
So, here it is. This is the ultimate challenge for humanity. The law of conservation tells us that the total amount of energy in the universe is fixed, and it is immense. The great human frontier, then, isn't about creating energy from nothing, it's about figuring out clever new ways to liberate it. I mean, if we could finally master thermonuclear fusion, the energy locked inside a single drop of water could power an entire city. The energy is there. The law guarantees it. It's up to us to find the key.